Hey guys, for calculus, this lesson is going to be from 4.2 throughout the beginning of 4.4. We're going to start making the connections of integration. Okay, so just to do a little quick recap and so we can know the clear difference between the four of these. When we're finding the area under the curve, we first started talking about Riemann sum. Riemann sum used a limit notation. And with the graph, we added the areas of all these little sub-intervals, specifically rectangles, and we found the total of their area and we added them together, okay? And this was our notation. We said that we would never solve it in this notation as long as we can convert it over to this integral notation, then we could finish solving it, okay? Then we started memorizing our antiderivatives. This was the reverse process of a derivative. That's going to come in handy when we start doing our indefinite integrals, which we saw last video. That's using antiderivatives to find the function that's going to be used to solve for the area under a curve. And now in today's lesson, we're going to start seeing definite integrals. So visually, what that does, so when we did the indefinite integral and we found that function, and you know what? I'm going to make sure that we even put, I'm so sorry, plus c. So when we did our indefinite integral, we found the possibility of some function here, right? Well, now when we have a definite integral, we're going to mark it off with a domain. We're going to say, okay, how much from here to here? And now we're going to be able to finish off and find an actual numerical value, okay? Now this formula here, very important. We're going to see it throughout this lesson. It's called the first fundamental theorem of calculus. Okay, and it's just basically that it was the pinnacle of calculus that you can find a total amount using a definite integral. And that finds the exact area under the curve under the given interval, okay? We use antiderivatives to solve this. So we'll go more on that in just a minute. The textbook says that if f, the function, is continuous on that closed interval from a to b, then f is integrable. Guys, it's a fancy word that just means you are able to do the integral, okay? So meaning that it exists, finding that definite integral, and in short terms, just make sure that the function is continuous between a and b. So if you have a function that, let's say in this scenario, has a discontinuity at 0, but the integral is asking you to look between, let's say, 2 and 7, even though there is a discontinuity, you are allowed to continue because 2 to 7 does not include that discontinuity, okay? So let's pick up on that fundamental theorem of calculus. Okay, it just says if f is continuous from a to b, then f has an antiderivative from a to b, then the definite integral from a to b of a function equals the antiderivative at b minus the antiderivative at a. Okay, so you'll hear me say a lot f of b minus f of a. So they're going to give you a function. The prime won't be there. This is just to say that you go from prime to the regular function. So the question will be asked like this. Your first step is going to be to find the antiderivative, and you're going to put a bracket from a to b. Okay, then once you find that antiderivative, you're going to plug b into that antiderivative, and then plug a into that antiderivative and subtract. When you are doing a definite integral, there is no need for a plus c. Okay, imagine if you had done a plus c, this function would have had a plus c, and you would have subtracted it with another function with a c. So having a positive c here and a positive c here with this minus would have canceled them out. So for that reason, anytime you do a definite integral, and again, a definite integral has these numbers here in the spot of a and b, you do not need to worry about the plus c. Let's look at this first example, okay? Step 1 is going to be to do the antiderivative, okay? So my first step is going to be the antiderivative here, okay? When I do the antiderivative, my exponent is currently a 1, so I'm going to add 1 to it, and it becomes an x squared. And I'm dividing 8 by 2, and I get 4. Minus, my current exponent is a 2, so it's going to become a 3, and now I divide by 3, so I have 1/3. And I'm going from 2 to 5. So again, that was my step 1, antiderivative, rewrite from a to b. Now I'm going to say my function at b, so I'm going to plug 5 into this, minus, I'm going to rewrite the function with plugging the 2 in. Okay, now if I do 5 squared, it's 25, times 4 is 100, minus 5 cubed is 125. I'm going to write that over 3. Minus 2 squared is 4. 4 times 4 is 16. And minus 2 cubed is 8. 8 over 3. All right, now you're going to make sure that you distribute that negative. So I have 100 minus 125 over 3 minus 16, and the negative make plus. Biggest mistake in these questions is people forgetting to distribute that negative over here and changing that sign. If I combine these two fractions, I get a negative 39. So I'm really working with 100 minus 16 minus 39, which gives me 45. So 45 units is the area under this function from 2 to 5. Okay? Let's try another one. Let's scroll up now that we have those notes down. So antiderivative here. It was a 2, so now it's going to be an x cubed. Divide by that 3. Minus, if I have a constant, it just becomes a 3x. And I'm doing this from 1 to 2. So now I'm going to plug in the 2 into the entire function. So I'm going to say 1/3 times 2 cubed minus 3 times 2. That's my f of b minus my function at 1, f of a. 1/3 times 1 cubed minus 3 times 1. And now I'm just going to clean this up. So 2 cubed is 8, so I have 1/3 of 8 minus 3 times 2 is 6. And when you get better at this, you can start taking 2 steps at a time. I'm going to clean, but I'm also going to distribute this negative. So negative 1/3 plus 3, okay? So then here I'm going to end up 8 over 3 minus 1 over 3 is going to be a 7 over 3. And then a negative 6 and a positive 3 is going to give me a negative 3. If I want common denominator, let's say this is on a non-calculator section, I'm going to multiply by 3 over 3. And I'm working with 7 over 3 minus 9 over 3. And I end up with a negative 2 over 3. So there are times you're going to be able to do this in your calculator, and I'll show you that at one point. But make sure you are comfortable doing this arithmetic by hand. If it's a free response question, once you are done with f of b minus f of a, so for example at this step, you would be done. You do not have to clean arithmetic in a free response question. So again, you do this step of the antiderivative, this step of the f of b minus a of, sorry, tongue-tied, f of b minus f of a, and you can stop on a free response. But on a multiple choice, you would have to get all the way down to that numerical answer. Let's check out that next one. I'm going to rewrite this integral. Feel free to, remember how in derivatives we just drop down that coefficient? You're going to be dropping down that 3. So if you feel more comfortable bringing the 3 to the outside and just doing the integral of x raised to 1/2, that is allowed. Because we're going to drop that 3 down and just do the integral here. So my exponent was 1 over 2. I'm going to add 1. So if I'm going to add 1 to 1/2, I get 1.5, which as a fraction is 3 over 2. When I divide by this new exponent of 3 over 2, I'm multiplying by the reciprocal, which would be 2 over 3. Okay. Oops, sorry, not supposed to put that there. I already did my antiderivative, so I'm not going to write that anymore. I'm just going to put a bracket. Okay. So I did my antiderivative. Now I'm going from 1 to 4. Just like you took that 3 out, I'm allowed to take out this 2/3. And the nice thing about that is that my 3 will cancel out with that 3 in that denominator. And now I could just take this 2 out. So what I'm really working with is a 2 on the outside. And then I'm going to do my f of b minus f of a with just x raised to 3 over 2. Okay? So now, leave that 2 on the outside for now. And we have 4 raised to 3 over 2 minus, there's my function at b, 1 raised to 3 over 2. Okay, now let's talk about these fractional exponents because you will be expected to do this on your own. The denominator is the root, meaning it's the square root, and the numerator is the exponent. So do you think it'd be easier to say 4 to the third power and then do a square root? Or do the square root of 4, bring it smaller, and then do the exponent of 3? So always try and make it smaller because the square root of 4 is 2, and then 2 cubed is 8. Minus 1 raised to anything is just 1. So what I'm really working here is 2 times 7, which this gives me a 14. Okay? Let's look at this next one. Antiderivative first. Antiderivative of secant squared is just tangent of x. Okay, I'm going from 0 to pi over 4. Okay, I did my first step. Second step is f of b minus f of a. So I have tangent of pi over 4 minus tangent of 0. Okay, now I told you that on a free response, you are done when you do f of b minus f of a. Now, that's true when, again, arithmetic is your only thing left. Adding, subtracting, multiplying, dividing, and exponents. But if I have a trig function, I do have to take one more step. So the tangent of pi over 4 is 1. This is unit circle. Minus tangent of 0 is 0. Please, if you're in my class, have your unit circle memorized. And then 1 minus 0 is just 1. And you're done there. On the AP exam, there are certain questions that are asked to be solved geometrically. So I'm going to use these first 3 examples to show you how they can be answered both with calculus and with geometry. As again, an integral, a definite integral is the area underneath that function. So this first question says the integral from 1 to 3 of the function 4. The function 4 is just a horizontal line at y equals 4, but they only want us to check from 1 to 3. Okay, so if I use calculus, my first step is to do the antiderivative. Antiderivative of 4 is 4x. Okay, I'm writing from 1 to 3. And then my next step is f of b, the function at b, minus f of a, the function at a. So then I end up with 12 minus 4, and I get 8. Okay? Now, if I want to do this geometrically, I see that this is so we'll put a little verses here, calculus versus geometry. This is a rectangle, we'll call it, okay? So the area of a rectangle, because again, this is the area under the curve, is base times height. In this case, the base is from 1 to 2 and 2 to 3. Those are 2 spots. And the height goes up to 4. So 2 times 4 is 8. Okay, same question, first solved with calculus, then solved with geometry. Let's look at this next one. Okay, I have a linear function of x plus 2, and I want to know the area under the curve from 0 to 3. So here it's drawn from 0 to 3. There's my linear function. Now calculus, I'll do the antiderivative. Add 1 to the exponent, I have x squared, divide by that new exponent, plus antiderivative of a constant of 2 would just be 2x. I'm doing this from 0 to 3. Next step, I'm going to plug my function. I'm going to plug 3 into my function, so f of 3 minus my function at a at 0. Whenever your second term has zeros plugged in and there are no trig functions, you can assume that all of this is going to cancel out because 0 times anything is 0, so you are subtracting by nothing. If 0 is in your first term, you need to be very careful not to skip that minus. And again, I was mentioning if there's a trig function in there, a trig function at 0 doesn't cancel out. It could be 1 or 0. So you have to be very careful with that. So now 3 squared is 9. I have 9 over 2 plus 6. Okay. And then I want common denominator. So I'm really adding 9 over 2 plus 12 over 2. 12 plus 9 gives me 21 over 2. Okay. Now, that was calculus. Let's look at geometry. This is a trapezoid. Okay. The area of a trapezoid is the average of the two heights. Okay. So height 1 plus height 2, and I take the average of it, and I multiply that, by the base. Okay. So my first height is up to 2. My second height is up at 5. Divide that by 2. And I multiply that by the base, which I go from 0 to 3, so I'm multiplying it by 3. Okay? Clean that up. I have 7 over 2 times 3. We can write that as 3 over 1. And I get 21 over 2. Same answer, two different ways. Calculus and then geometry. Let's do one last one. Okay? I have not taught you yet how to do an integral that has a composite function. By composite function, I mean inside of this radical, there's more than just a simple x. Okay? So, the calculus has not been learned yet. So there may be a time where there's a method that you have not learned because maybe it's in calculus BC, and on the AB test you'll be expected to still be able to solve it, but with geometry. Okay, so geometrically this is a semicircle. Okay, the area of a circle is pi r squared, but since it's a semicircle, I'm going to multiply it by half. Okay, now my radius is right here. It's a radius of 2. So I'm going to say half times pi times my radius, which is 2, squared. 2 squared is 4. Half of 4 is 2. So I multiply that 2 with a pi, and my area underneath this semicircle is 2 pi. Before we close up this video, I want to show you some quick properties. Okay, so I've drawn for you here that typical image we show with a function and the area that can be drawn under that curve from A to B. The first property says that if the A to B has the same number, we can assume that the area under the curve is 0. So imagine if I was trying to find some space underneath this curve from A to A. Since I'm not moving, I'm not actually finding any space, okay? And that's why the area under the curve from A to A is just 0. I don't have anywhere that I'm moving over to, okay? So if we look at this example, if I say the integral of sine of x from pi to pi, the moment you catch that these two are the same number, you don't even have to show any work. Property says that this equals 0. Now, if you were to do the math, let's say you don't catch it, don't stress it because the math will give you 0. For this next property, it's not mandatory that you use it, but there's going to be another property in calculus that there's going to be a certain time when you do have to use it. But do not feel that you have to use it every single time. So let's take a look at this one. Notice that we've always said that the integral is from A to B. The smaller number goes on the bottom and the larger number goes at the top. If they flip it and they put from B to A, the larger number at the bottom, you are allowed to switch the location of these two numbers as long as you pull out a negative, okay? So I'm going to solve this one as is, and then I'm going to pull out that negative and solve it, and you're going to see that it gives you the same answer both ways, okay? Antiderivative here, add 1 to the exponent, it becomes x squared, divide by that new exponent, plus antiderivative of 2 is 2x. I'm going to solve that from 3 to 0. Okay? Remember how I told you if the 0 was first, don't skip it completely. I have half times 0 squared plus 2 times 0. Minus, now I'm going to plug in that 3, half times 3 squared plus 2 times 3. If you would have forgotten, like let's say you think, okay, I know that 0 plugged in is going to completely cancel out and you don't write it, I fear that you will forget that minus. So be careful. You can just put one big 0 here if you'd like, but do not forget that subtraction. Okay? So I'm going to have a negative that I'm going to have to distribute. And then I have 3 squared divided by 2. Okay? 3 squared is 9 over 2. I'm going to distribute that negative while I'm at it. Negative 9 over 2. And then distribute that negative minus 6. Okay? Get a common denominator. And I have negative 9 over 2 minus 12 over 2. And here I get negative 21 over 2. Okay? Now, let's use that property. The property says I can flip this order, take out a negative, and be writing the integral from 0 to 3. Okay? Let me draw a line here so we don't mix it. So, I'm going to pull out that negative here. Antiderivative is the same antiderivative here. But now I had flipped it, so from 0 to 3. Okay? So I have this negative on the outside, be careful. And now I plug in that 3, half times 3 squared plus 2 times 3, right? And then minus, if I plug 0 into all of this, you can start getting a little quicker at this. You know that whole thing is just going to give you 0, okay? And then now this part cancels out. And now I just distribute my negative. And notice at this point, I have the exact same thing that I had right here. Okay? So if you finish cleaning this, it's going to be that negative 9 over 2 minus 6, get common denominator. Negative 9 over 2 minus 12 over 2. The rest is the same. Negative 21 over 2. Okay? So if you see a regular integration, you are not forced to flip it. The property does get asked individually on the AP exam. And coming up, we will be learning about the second fundamental theorem of calculus, and it may become necessary at some point then. Okay? But if it's a regular integration like this, do not feel like you have to do it. All right, last property for this video. You are allowed to split integrations. This is very popular in the AP test to just be asked as a property. And basically what that means is if I have an integral from a to b, right, from a to b, if for whatever reason I need to split it, let's say in this graph, I need to for some reason split it here at c, I can then do the integral from a to c, right, find that area under the curve, which is what I'm doing here, and then add it with my area under the curve from C to B. Okay, so hopefully visually that makes a little more sense to you, that you are allowed to split it and then just add it together, right? And that C to B is this one right here. So the reason why that starts to become useful is because of functions like the absolute value of x. Absolute value of x, right? It's a v. And remember, sharp turns, I have an issue with sharp turns, okay? We've talked about this before when we talked about differentiability. And if it has an issue with differentiability, sharp turns, it also has an issue with integrability. Fancy words, it just means you can't do the integral at that point. So if I can't do the integral at that point, I can split this, right? It's from -1 to 1. Let's just do a quick little visual here. By the way, hopefully your eye is catching that you can do this geometrically. I have 2 triangles, totally doable. But what I'm going to do is I'm going to split it from -1 to 0 and then from 1 to 0. Okay? So when I go the integral from -1 to 0, this is just, remember, absolute value means is that I can do a negative and a positive. So from the left to 0, it's the negative x function. And then I'm going to add it with the integral from 0 to 1, and that's a positive slope, so that must be the positive x dx. Okay? Understanding functions and their graphs and what they look like really helps out here, okay? So something nice to do is that negative, I'm allowed to take it out here. And the reason why I want to do that is so that my work becomes a little easier. I'm doing the same exact antiderivative. Okay? Antiderivative of x, I'm going to add 1 to the exponent and divide by that new exponent. Okay? This one goes from 0 to 1. This one goes from -1 to 0. I'm going to add those answers, but this one has a negative sign that was pulled out. Okay? Now, remember I told you you're allowed to also bring out those coefficients. So I can say -12 and then do the f of b minus f of a for x squared from -1 to 0, plus take out that half. So I have less arithmetic to do and go from 0 to 1. Now I'm going to do my function at b minus my function at a plus half times my function at b minus my function at a, right? These zeros are going to cancel out. Be very careful with those negative signs. That's where the biggest mistakes happen here. And now I have -12 times a -1 squared is a positive 1, but I still have this with negative down here. And then 1 squared is just 1. So a negative and a negative make a positive. I end up with half plus half, which gives me 1. All that work for a 1.